right, so we're looking at percent exponential growth and decay in this lesson. The very first box that we're going to do, the first slide, is review. This is something that we've already done. That way we'll kind of have in our minds what we know, and we can link that to what's going to be new. All right, so it says a population of 10 hamsters will triple every year for 4 years. What will be the population after 4 years? We're going to do a couple of different things. We're going to write an equation, or you could call it a function, and then we're also going to set up and use that equation to find information. So to start off with, in this box, we're going to put the main formula A times B to the T power. Sometimes it's T, sometimes it's X. That's the basic format we've been using. We've talked about it before. A is always your starting value. So in this case, that's going to be 10 because we're starting with 10 hamsters. Okay? B is what we call the multiplier. It has different names. Sometimes they call it the multiplier. Sometimes they call it the growth factor. It's basically that number that's the pattern. So if it's tripling, what are we multiplying by?
3.
3. So in this case, that's going to be 3. And then T is your time. And in this case, it's in years, and we're going to have 4 years. So we'll put that in. So we're going to write an equation for the situation first before we put in the force. So just a general equation we could use for any year. Go ahead and help me out. So it'd be y equals
10 parentheses 3
to the t power. So this is just the equation. I'm going to put t in there. I want to have an equation because they might ask me 4 years and then 10 years and then 17 years. Because I'm explaining that right now. Listen with your ears. Okay? So we're going to write an equation first that's generic, that we did not put the 4 years into, and then we can put the 4 years to answer the question. The reason why is because on your homework, they're going to ask you for 3 or 4 different time periods. So you're going to do this first, and then I'm going to go, okay, so what if time is 4? We can go ahead and do that. So 10 times 3 to the 4th power. So we do the power first. So 3 times 3 is 9, times 3 is 27, times 3 is 81. So this would be 10 times 81, which would give us 810 happy hamsters. We don't know if they're happy, but hamsters. You could also use your calculator to do this. 10 times 3 to the 4th power. Your calculator will take care of order of operations for you, but I didn't really necessarily need it for this problem. So this is review. So on your homework, they're going to ask you to write an equation. Sometimes they're going to call it a function. You can use function notation or not. If you just want to use y, that's fine. And then they're going to ask you sometimes 1, 2, 3, maybe 4 different time periods. So you might have more than one of these to do. So that's why it's good to have this set up just as a generic to start with. Okay? So now we're going to take a look at what if we're not growing by, like we've done a lot of problems where it's doubling or it's tripling or it's taking times 5. But what if it's growing by a percentage and not by whole numbers? We haven't really done that. So we're going to talk about that in the next box. Okay? So we have a deposit of $1,500 in an account, pays 7.25% interest compounded annually. How much will be in the account after 8 years? All right, so if we're just thinking about that general y equals a times b to the t, what's our starting value? $1,500. We're starting with $1,500. Okay, and then the multiplier is a little tricky. So the first thing I'm going to do with this is I'm going to take this percent and change it to a decimal. So it's 7.25 would be 7.25%, right? And so I changed the fraction to a decimal, but now I need to change the whole percent to the decimal. You guys remember the Dr. Pepper thing we learned before? How many places do I move the decimal? 2. So I move it back 1 place, put a 0, move it back another place, put a 0. This is where my new decimal point is.
Wait, what was the Dr. Pepper thing?
Okay, so Dr. Pepper, if you're going from decimals to percents, you go 2 places this way. If you're going from percents to decimals, you go back 2 places this way. So it was something that we talked about earlier in the year. But basically, it's just to help you remember two places. Now, if you're doing interest, this is going to add to what you already had. So the percent we started with was 100%. So we're going to take this number, the 0.00725, and we're going to add it to 100%. How do you write 100% as a decimal? Go ahead. 1. So I'm going to add it to 1. I'm just going to put a 1 in front of it. So then my multiplier is 1.00725. Because you start, basically what we're doing is we're taking 100% and adding the 7.25% to it because it's growing. And so 100% is 1, and the 7.25% is the 0.00725 that we just did, and you add it together. So this right here is my equation. And then if they want to know how much it is after 8 years or 10 years or 20 years or whatever they're going to ask, all I have to do is now put that into my equation. So I'm going to do 1,500 times 1.0075 to the 8th power. So you can just type all of that in. So let me show you what that'll look like on your calculator. Let me get that up where there's a little light on it. So you do 1,500 times 1.0075. You can put it in parentheses or not. And then you hit your power key.
Forgot the 2.
Power key in the 8th. What 2? There's no 2.
0.25.
No, it's 0.75.
Oh. What? Oh.
Okay, and I accidentally hit the divide key instead of the power key. This is what it's going to look like. You use your little caret key for the power. 1,700 times your multiplier to the 8th power. You hit enter. And we're going to round off to money. How many decimal places do we need for dollars?
2.
So I'm going to look at the 9 then. Does the 9 round up or does it stay?
It stays because it's...
So the next number is an 8.
So it rounds up.
So it's going to round the 39 up to 40.
Oh, I thought we were doing the 15. Oh,
So we're rounding it off to the nearest penny. So we're going to actually write down...
I thought you were going to put the decimal in between the 1, 5, and 9, 2.
No, because that's already our whole number. So it's 0.398, so that rounds up to 0.40. So hopefully they're going to give us that extra penny and round it up. And so that's my final answer.
When did you eliminate 725?
Okay.
Like eliminated
She added
the 2.
it. Okay, so
So that point, there is a 2 in there. So
I knew it.
725. All right, I get what you're saying. I just didn't see it. So 725. So we'll just retype it. 1,500 times 1.00725 to the 8th. So it's just a tiny bit bigger. So it comes out 1589.24 because you get 0.2399. So I round the 3 up to a 4. All right. Sorry about that. We all make mistakes. It's just a little bit more embarrassing when you're doing it in front of a crowd and you're recording it.
And you're math teacher.
And I'm the math teacher. All right. So let's go ahead and look at, we're going to give you guys a formula for percent increase. Okay, so if A is your starting value and R is your percent increase and T is your time, this box really isn't big enough, but I'm going to try. You do A parentheses 1 plus R percent to the T power. So my T is the only thing that's not going to fit in the box. So this just kind of sums up what we just did. So if I'm adding a percentage on, I always add it to 1 because that's your 100% that you started with, and then you're adding it to that. If you don't have the 1,
Does that say R over 1?
it says R percent. Let me zoom in. R percent. So that's a percent sign. Okay? And then to the T power. So we're going to try another problem. It says, a colony of 10,000 ants can increase by 15% in a month. How many ants will be in the colony after 1 year? Okay, so 10,000 ants is going to be our starting value, so that's A. So the part that we usually think of as B, on here, they're telling us to do 1 plus the percent. So first of all, I have to change the percent, 15%, to a decimal. So my decimal point's right here. I'm going to take it back 1, 2 places. So that's the same thing as 0.15. And then I'm going to add 1 to it. It just makes it 1.15. Okay? So if I'm just writing the equation, I would do y equals 10,000, 1.15 to the t power. Okay, I didn't ask for it, but it will on the homework, so I'm just making sure we do that. So this is what we call the multiplier, okay? And then if I want to know how many there will be after the first year, then my power is just 1.
11,000.
So 10,000 times 1.15 to the first power, and what does it come out to be?
11,500.
11,500 ants. Just makes me feel creepy. All right. So, and then if they ask me 2 years, 3 years, 4 years, I could just put in those different powers, but I have this equation to start from. Okay? I don't have to make like a new problem each time. It's just I'm putting different numbers in for the time. So on the homework, it's going to ask you to write the equation, or it might say function, and then they're also going to give you different times to put it. All right, so what if there's a percent decrease?
Then wouldn't it be decay?
It would be decay. Good job. And then we're going to talk about what the equation looks like. So you're going to have A, instead of adding 1, you're going to take 1 minus the interest, the percent decrease, and then you'll take it to the t power. So A is still your starting value. R now is your percent decrease, and T is your time. So you have to subtract it instead of adding it. All right, so a radioactive material decays at 10% per year. So it even uses the word decay, so good job. How much of the 12-pound material will be left after 20 years? So instead of doing a half-life, they're giving us a slightly different number and talking about it in a different way. So what's our starting value? 12 pounds. Okay, so we know that that's A. And then to figure out our multiplier, we're going to take 1 and subtract 10%. How do I write 10% as a decimal? 0.1, right? Because we're going to take this back 2 places. So I'm going to have 1 minus 0.1. And so basically I'm taking 100% and subtracting 10%. So what's going to be left? 90%, which is 0.9. And that's going to be my multiplier.
Why do we have...
So if it's decreased, you're going to subtract it from 1.
I get that.
Okay. And we've changed percents to decimals before. You just move it back 2 decimal places. Okay, so let's talk about that just a little bit. So we're starting with 10%. Your decimal's here. We just moved it back 1, 2 places, put it here before the 1.
That.
Okay.
I just don't know why we have to keep it in decimal form.
Because your calculator doesn't have a percent key. So we have to use decimals. All right. So for our equation, we're going to have y equals. Our starting value is 12. Our multiplier that's going to go in the parentheses is now 0.9. And if you think about it, that makes sense. If 10% is decaying, 90% remains, and that'll be to the t power. So what we're really doing is figuring out how much is left that's still radioactive. Okay? So then, to figure out how much is left after 20 years, instead of doing the table like we did on those growth and decay things before, I can just take 20 and put it into this. 12 times 0.9 to the 20th.
1.458919.
So 1.458. So I'm just going to round that off to about 1.5. So 1.5 pounds is still radioactive after 20 years, which isn't very much if you consider you started with 12 pounds. Okay?
Hold on, don't move.
So instead of doing a half-life and telling us when it's going to be half, they're telling us how much it's going down each year, which is basically going to give you about the same answer, but it's set up a little differly.
Thank
Okay?
God you gave this to us on a Friday, so we have all week to do it.
We're recording all of your whining right now, so please stop. Okay, so let's move on to the next problem. All right, so a baby weighing 7 pounds at birth may increase in weight by 11% per month for the first 12 months. Babies in the first year grow percentage-wise more than you'll grow for the rest of your life. They just grow really fast. So it wants to know how much the baby will weigh after 1 year. Now this is tricky because here they're talking about months and here they're talking about a year. So we need to keep thinking that my time for 1 year is still 12 months because it's talking about 11% per month. So if that's how often that 11% is getting added, I need to make sure that I'm thinking about everything in terms of months. So you might have to change some of those times so that they're all on the same time units. All right, so the baby is starting off at 7 pounds, so that's our starting value, and it's gaining 11% per month. So let's just talk about the multiplier for a second. So our multiplier, we add 1 plus the 11%, okay? So how do I write 11% as a decimal? Move it back 2 places. So I'm going to have 0.11. You're just moving it back 2 decimal places. So that means I'm going to use 1.11 as the multiplier, okay? None of this is anything really new. It's stuff we've done. We're just combining it into one lesson. So our equation then is y equals, the starting value is 7. We're multiplying it by 1.11 to the time period. So in theory, I could figure out about how much the baby would weigh at 5 months or 8 months. Not all babies are going to grow the same amount. They'll have little spurts. But this would give you an idea of whether or not they were on track. Okay? So if I want to know how much it is after 1 year, that's 12 months, which we talked about. We converted it to months. And so we're going to put in 12 up here. So it'll be 7 times 1.11 to the 12th. And we get 24, so I'll just show you my calculator. We got 24.48. Since this is pounds, I just round off to 0.5. So it's going to be about 24.5 pounds when they're a year old. It's not going to be perfect for everybody, but this is just something they'll take lots of statistics from babies all over the world, millions of babies, put it in a database, figure out if you have the starting value. You can kind of figure out about where they should be at a year, and then you'll know if somebody's growing at the right rate or not. And then they have some general, okay, if they're within a range, which I'm not going to talk about today. Okay, so get it all written down. Give you about a minute. And if you don't get it all, we can always go back and copy it down later. Okay, get it. We're recording. All right, so here's the last box. Find the value of a downtown office building that cost $12 million to build 20 years ago and depreciated at 9% per year. So basically what they're saying, if it depreciates, that means the value goes down. Yeah, so your value is decreasing. So evidently this building is getting old and nobody's making improvements on it. And so if you don't maintain something and make improvements, it loses value, okay? So we are not going to write all the zeros out for the million. We're just going to use 12 as our starting value, and then we'll write million on our answer. As long as we remember to write million on our answer, we'll be okay. And then it was 20 years ago, so that's going to be our time here in a little bit. And then we're going to use 9% as our decrease. So we're going to take, for our multiplier, we're basically going to take 100% minus 9%. Let's think about that first. Would it be easier if we just took 100 minus 9 and wrote it as 91% first and then changed it to a decimal? Do you guys like that better?
Yes.
Okay, so then if we change it to a decimal, you'd move it back 2 decimal places. That's the same thing as 0.91. It's the same thing. It's just a matter of, are you changing it to a decimal and then subtracting, or subtracting and then decimal? Either way. So if it's losing 9% of its value, that means it's keeping 91% of its value each year. All right, so let's set up our equation. Y equals 12 is our starting value. Our multiplier is 0.91. And then we're going to go ahead and just write it with a t there to start with, because that's our equation. You could also call it a function. It's considered an exponential function. So basically, this 100% was the 1. We're taking 1 minus 0.09. and that's where the 0.91 came from. When it's decreasing, you subtract from 1, which is the same thing as subtracting from 100%. So we still have the 1, we just did that up here. All right, so then if we want to know after 20 years, it was worth 12 million 20 years ago. We want to know how much it's worth now. We're going to go ahead and put 20 in for our time. So we started with the 12 million. We're just going to use 12 to represent that. 0.91 and then to the 20th power. So I'm going to put that in.
1.8.
So 12 times 0.91 to the 20th. And so we'll just keep maybe 1 decimal point. So this would be 1.8, and we'll write it as 1.8. We got 1.819738. Okay, so we're going to round that up to 1.8. We're going to put a $sign on it, and then remember that we started with 12 million. That means this is 1.8 million. It's actually 1,800,000 ish. And so since we didn't put all the zeros down for the million, it's not $1.80. We have to make sure we're putting the million on there. It didn't depreciate that much. That would be much more than a 9% decrease. All right, that wraps it up.